going to pick up where we left off in the middle of page 42, section 4.2. We went all the way down to the formal addition rule. Before we go on, just a quick reminder. When we are doing probabilities with A or B, like the examples we were doing last time, that's when we add things. We either add them by counting the numbers in the table like we did last time, or you use that formal addition rule that has adding. That or tells you to add. That's going to be really important because in a little bit we're going to be multiplying, and you need to be able to understand when you read the words for probability when you add and when you multiply. So when there's an or statement, this or that, we added the people that are in this category or that category and so forth. Or means add, yes, that's what we're trying to get across. Okay, disjoint events cannot occur at the same time or there is no overlap. An example of disjoint events. You cannot be late to work and early to work at the same time. I don't think that could happen simultaneously. Those are disjoint events. But you could be late to work today and early to work tomorrow. Those both could happen. When we say the same time, could they both happen? I guess those 2 different days. But it's possible that you could be late today and early tomorrow. So those would not be disjoint. So there's no overlap in the first one, but they could overlap. Both things could happen. Can somebody come up with 2 other events that are disjoint, things that cannot happen at the same time?
Here and there.
I didn't hear you.
Here and there.
Yeah, you can't be here and there at the same time, right? I'm here and she's there. We can't be both places. If you flip a coin, I dare you to get heads and tails. You get heads and then you flip it and you get tails, you flip it at the same time. So those are disjoint. The reason we care about disjoint is there's no overlap. Remember the formal rule that we talked about? You could just count, or you could do the formal rule, which looks like this. It's right above where we're talking about. That was the formal rule written right up above where we're starting right now. What does this mean? What's that mean? Sorry, I can't read it, Kirsty.
No, I can't.
P, A, and B. Somebody's got to be awake today.
You subtract them or not double count.
Yeah, we add, when you're looking for the probability of, for example, being late to work today or early to work today, late or early, I would add the probability of being late plus the probability of being early minus the probability that I was both early and late. In that specific example, is it possible for me to be both early and late in one day? No. So that part that you subtract would be 0. That's why we care about things that are disjoint. If there's no overlap, this part would always be 0. It's impossible to do both A and B. That's why we care about disjoint. All right. Complements are disjoint, which is one of the examples I gave you. Complements are disjoint. Let A, remember the die we were rolling last time, the 6-sided die? Let A be the event of, what we have? We had, let's say, rolling a number greater than 3. We'll make a new one. So I'm rolling a 6-sided die. Bless you.
Bless you.
So this is A, rolling a number greater than 3. What is the complement of that? Remember we write that with a bar over it? There's some words we would use to describe the complement. Yeah, but this specific example, what would the opposite be?
Less than 3.
Less than 3?
3 or greater. 3 or less.
3 or less, we gotta be careful here, right? Which one is it?
3 or less.
It's 3 or less. We can't just say, what would happen if we said less than 3?
Because 3 wouldn't be accounted for.
3 wouldn't be in there anywhere, right? You have to have everybody accounted for. We're not leaving anybody behind. I was talking about this in my other class. She's like, oh, Hannah, we can't leave anybody behind. So rolling a 3 or less? we agree these are complements? Every possible outcome is either in this group or in this group. Are they disjoint?
There's no overlap.
There's no overlap, so then they are disjoint. Disjoint means there's no overlap. So they don't overlap, which means they're disjoint. The complements have to always be disjoint because they're supposed to be opposites, right? You can't have the same thing. So then underneath here, let's figure out for this specific example, the probability of A plus the probability of A complement. For this specific example, so a little review question. Remember these were the 6 things that could happen when you roll the die? Those of us remember dice? What is the probability of rolling a number greater than 3?
25.
1/2.
1/2? How'd you get that?
3 over 6.
3 over 6. So let's break that down. There's 6 possibilities. Time to wake up. No more excuses. There's 6 possibilities, and how many of them are greater than 3? 3 of them, right? 2, 4, 5, and 6 are the ones that are greater than that. Plus the probability of A complement out of 6. How many numbers are 3 or less?
3.
A different 3 out of 6, right? What do these two add up to? 1. 6 out of 6, which equals 1. That is true for anything that we do. Any event and its complement. So this is what you want to fill in on that little line that you have there in your notes. If you flip back to the page where we talked about getting hit by lightning, see where that was? That was on page 39. Page 39, we did that problem last time, where we found A was the event of being hit by lightning. What did we find for the probability of getting hit by lightning as a decimal? Anybody have it in their notes? Back on page 39.
It's 0.0006 zeros, right?
Yes.
And a 966, 364, 158.
I'll just round it to here. Is it round to 96 if I was listening correctly?
It'll be 97.
97? Thank you. I didn't hear what came after it. This is lightning. I'm gonna put a little note here. This is the lightning problem from page 39. Just pointing out this how this works. We've already actually done this. So this was the probability of getting hit by lightning. What's the complement? Not getting hit by lightning. We did that one also. What was that? A bunch of 9s. Help me out. 6 9s and then
0337.
0337. So I would round it, well, right here. There. So this was the probability that we found last time. I got 2 decimals there. Of being hit by lightning. This is the probability of not being hit by lightning. I dare you to add those up. Guess what they add up to? They add up to 1. Why?
Because probability is only from 0 to 1.
Because probabilities are between 0 and 1, but why does it add up to exactly 1? What does 1 mean with probabilities?
It's likely.
It's
It
even
will
stronger.
occur.
It will occur. I am guaranteed that today I will either get hit by lightning or not get hit by lightning.
It's pretty funny because there was a wicked lightning storm
I-
at 5 this
It
morning.
wasn't there though? It woke me up this morning.
It was cool.
It's true.
Somebody
Because
did
today,
get hit by
I'd
lightning.
watch it.
Yes.
Yesterday, someone got hit.
really? Scary.
Yeah.
But no matter what, luckily none of us got hit that I know of. Well, let's go back to the point. I have my great example on the perfect day. If we were talking about chalk. Okay, wait, let's pull it back together, guys. These people watching the video don't want to hear us chat about lightning. Either I will get hit or I won't get hit. I'm guaranteed, right? I'm guaranteed that one or the other will happen to me. Either I'll get hit or I won't. So of course it's 100%. Complements will always add up to 1. always. So the probability that when I flip a coin I'll get heads or tails is 1. I've never seen anyone land on the edge. I've heard people talk about it, but I've never seen it happen. So what if I want to find the probability of A? Here's where a little bit of algebra comes in. If I'm using this formula here, and you want to solve for the probability of A, solve this equation for the probability of A, what would I do? I'm trying to solve for this part. Or I get this by itself in the equation.
You subtract.
Ooh, I gotta be careful, I got addition here.
You
So,
subtract.
so I would subtract this to the other side, minus this and minus this on both sides. Do we agree that this is the same statement, just written a little bit differently?
Yes.
One of them is 1 minus the other. Right, they add up to 1, and you know one of the events, the complement's gotta be 1 minus the other one. And similarly, guess what the next one is? Going across your page there. Probability of A complement. What do you say? 1/2 for this example, but I'm talking about in general, just using this formula. Same way I did that one.
It would be 1 minus P A.
1 minus P of A. So let's interpret this. The notation looks scary, but what this says is if you want the probability of some event, you could take 1 minus the probability of its complement, and then you would be able to find the answer. Or, if you're looking for the probability of the complement, you could take 1 minus the probability of the event. Now those formulas look all scary, but let me give you a simple example which I think you can handle. Let's say that the probability that it was supposed to rain today was 0.30, meaning there was a 30% chance of rain. What's the probability that it won't rain? People are telling me it's 0.7. How are you getting that?
It has to equal 1.
It has to equal 1. Remember, because those are complements. So if it has to equal 1, 1 minus that number is 0.70. So if you know one of them, you can always find its complement by subtracting from 1. A lot of people can do this easier if you think about them in terms of percents. If there's a 30% chance of rain, some of us already subtracting in our head. 100 minus 30 is 70%. But we just leave them as decimals when they're probabilities. So we okay with those 3 formulas? Okay, so we're going to move on and do a new example. Now we're going to flip coins, and we're going to start guessing on a multiple choice question. So at the bottom there, we're flipping a coin, and we're guessing on a 5-option multiple choice question. So imagine that you have Scantron, it's got 5 bubbles, and one of them's the right answer. That's what they're talking about. I'll actually draw a picture of my little Scantron here. Maybe it's number 1 on my whole quiz is 1 Scantron quiz. Here's my 5 little bubbles. And you're going to pick one of those, right? A through E, whatever it might be. Maybe we'll even they usually have letters, right? I think they do. I don't give Scantron tests very often. So you're going to guess, because I didn't tell you the question, you can't read it. If you talk during the test, you get in trouble, so you're just going to guess. Okay, so you're going to flip a coin, and then you're going to guess on this quiz question that you can't tell what it is. Let's decide in advance which one's right. Which one do you want to be the right one?
C.
C? C for correct, I like that. So it turns out that this is the right one. C is the correct answer. Now that we guessed, it would have been nice to know that in advance, right? So if you happen to guess C, then you got the points. If you didn't get the points, right? C is the correct one. Okay, so let's look at these questions at the bottom. Find the probability that the coin shows heads, or you correctly guess the correct answer of the question. There's the question. What are the options for my coin? Heads or tails, right? I'm going to put it here, here's my coin. Heads, tails, those are my only options. So the question says, what's the probability that the coin shows heads, or you correctly guess C in this case. Why is this hard? Yes.
Is it just 2/7?
Is it 2/7? No, it's
About
not.
two, like, possible.
No, it's,
Yes?
so you said when it's or, you have to add, and then so it would be P and then 1/2, or P and 1/5, and then you add them together and you get 0.7.
Probability of, was it tails or heads? Probability of heads, you're saying, plus the probability of correct guess? Is that what you're saying?
Mhm.
So let's go with that for the moment. We're gonna go back to Hector's 2/7 in a second here though. What's the probability when I flip a coin it'll be heads?
1/2.
1 out of 2, right? One of the two sides has heads on it. If I'm guessing on this quiz question, what's the probability that I'm gonna guess right?
1/5.
1 out of 5. But, the formula says, add the probability of one, plus the probability of the other, minus any overlap. Is it possible that I might flip heads and guess correctly?
Yeah.
So there's some probability there that I need to subtract. Uh-oh, what is it? I don't understand why, I expect you to be slightly confused right now. I expect you to be slightly confused, because there's something that we're missing.
Oh, is it minus P heads and correct?
Yeah, the problem is, we need to figure out how to get that. Let's write it in here though. The probability of heads and correct, so that could happen, so we have to subtract this probability. The problem is, we don't know how to get it.
Would the head still be 1/2? Because it's still a half chance that you get heads or tails, right?
But it's the chances that I'll get heads and guess the correct answer at the same time. There's something wrong.
Oh.
We're getting to the multiplication rule. So some people may have seen some probability before. It involves multiplication, but we're not even gonna do that quite yet. We're getting there.
Is that one 2/7?
Nope, that one's not 2/7 either. Why is he saying 7, by the way? Because he's counting how many different outcomes there are, and our denominator is how many outcomes. There's more than 7, which is why we're kind of stuck and we can't figure this out. Let's list the sample space for this scenario. What's the sample space?
All possible things.
All possible things that could happen. Okay, so here we go. We're gonna list my sample space for this problem. Is there room for you to squeeze it off to the side maybe? There's going to be 10 things in my sample space. I might flip heads and then guess A. That's one thing that could happen. My coin shows heads and then I guess A. Or,
Heads
No.
and B.
I heard tails and A and heads and B. Depends which way you go. Heads and B, or maybe I'll come over here. Tails and A. I'll try to be organized here. Or I might flip heads and guess C. Or heads and D and heads and E. Those all could happen. And similarly over here, the same thing but with tails. Don't lose my spot. Is there anything else that might happen? These are all possibilities, right? There's 10 of them, which is why it's not 7. We think it's 7 because you've got 5 choices and 2 things, but because they're going on together, there's more combinations of them. So now I think we could actually finish this. Based on that sample space there, what's the probability that I'll get the heads and the correct answer? How many of these over here have heads and the correct answer?
1.
Just this one right here, right? Here it is. That's the only one that has heads and correct? 1 out of 10. Minus 1 out of 10. You have to get a common denominator, or you can use your calculator if you don't like that, or you can change them to decimals, whatever you want. Let's see what that'll be. Can't do it off the top of my head. 6 out of 10? Someone doing that in their head? Should I write it all out? You got 6 out of 10? If you do a decimal, it comes out 0.6. If I was doing common denominators in my head, if you want to keep fractions, this is 5 out of 10, this is 2 out of 10, this is 1 out of 10, which is where we got the 6 out of 10. Or you could have turned them all into decimals. 3/5. I want to reduce, because I like my fractions reduced. So if you're guessing on this quiz question, and you're flipping your coin, 3 out of every 5 times you do this, you'll get heads or the correct answer. Yes,
I got 8 out of 10.
you got 8. I got 5 plus 2. This is 5 out of 10.
Yes.
This is 2 out of 10. So 5 plus 2 is 7. And minus the 1? Because we're subtracting?
I kept adding.
Ah, yeah, we're minus because remember we're subtracting the overlap. Questions? Remember I told you last time that probability is about to get hard? It's getting there already. But here's the good news. If we had drawn our sample space first, this problem would have been so much easier because I wouldn't have had to use the formula. Let's come back over here to my sample space. What was the question? Oh, it's been 20 minutes now. What was the question? Question was heads or you guessed the answer correctly. Let's circle all of the ones that are heads or a correct answer. How about this one? Is that one good? Does this one have heads or correct? Or doesn't mean and, guys, careful.
Yes.
Heads or correct? Yes, because there's heads in there. It has heads or correct, it has heads. How about this one?
Yeah.
Yeah, again, heads or the correct. This one has both. It has heads and correct, so it has one or the other or both. How about this one? Yeah. All of those get circled because they all have the heads in them. What about over here? Which ones might I circle?
TC.
TC, I heard. Why that one?
Because you have the correct answer.
It has the correct answer. So I've circled all of the ones that either have heads or the correct answer. How many of them have I circled? 6 out of the 10. You wouldn't have even had to do the formula. Remember we talked about slightly above the page there? You can either just count and do the intuitive rule it's called, or you can use the formula. If you ask for help on my stat lab, it's going to tell you to do the formula, which is doable, but it's a little bit more complicated in my mind. The trickiest part is our brains want to think and when the question is or. So some of you were saying, no, that one's not it, but it's an or. It has a heads or the correct answer. So that was all for that very first question. You okay over there? Questions? Okay. What's the next one? What's the probability that the coin shows heads or tails? Oh, yes, sir.
I have a question real quick, just because I'm confused. But why is it 1/10 instead of 2/10 when you can get like heads C and tail C?
When I subtracted right here?
Yeah, like why is it
But is this the 1/10 you're talking about?
Yeah.
So this 1/10 right here was talking about heads and correct. And.
Okay.
That just answered your question?
Yeah.
Oh, okay. And there's only one way to do that.
Thank you.
You're welcome. Other questions? Okay, so the next one, so easy it's hard. The probability that the coin shows heads or tails?
1.
1. Why is it 1?
Because it has to show heads.
It has to show heads or tails. You're guaranteed it's going to be one or the other.
Sorry, 99.7.
What'd you say?
99.7.
99.7? No, even more than that.
That's crack.
So it's 1. Until someone actually shows me they can land on the side, it's not going to happen. Okay. And then the last one, the coin shows tails or you have an incorrect guess on the question. So tails or you guessed wrong. Tails are wrong. I heard 9 out of 10? How'd you get that? Bless you, Kat. I'm allergic to probability.
Because there's.
Let me pick up the rest one. tails or wrong? We know there's 10 things to choose from, right? So now we just need to go over there and count how many of them either have the tails in them or they have the wrong answer. 9 I'm hearing. Let's make sure we all see where the 9's coming from. See if I can erase all my blue marks and make new ones. Oh, it's probably impressive for me. It literally locked them. So I'm going to circle all of the ones that are either tails or they have the wrong answer. I'm going to say it's an or.
It's 80.
I'm automatically going to circle this whole column over here because they all have tails, right?
Yep.
All these guys all have tails in them. They all have tails or the wrong answer or the right answer, but they, for sure they have tails. How about over here? Which ones am I going to circle over here?
A, B, D,
All of the ones that are wrong, which is everything except
A, B.
this one, because that's the one that has heads in the right answer. Pull that door shut, please. Thank you. So what's the answer? 9 out of 10, or 0.9 if you're doing decimals. Yes. You mean decimals or fractions? I don't care either way. When you're doing the MyStatLab, it'll tell you it wants you to put a decimal and round it or leave it as a fraction. Most of the time I leave mine as fractions unless they're so big and ugly that you can't really tell how big or what they really means. Then sometimes a decimal makes more sense. But I'm not that picky about it. Yes.
Before where it says P of the coin shows heads or tails, what was that? It was 1?
The answer is 1.
Okay, 1.
Because when I flip a coin, will it show heads or tails?
Oh, because the probability is showing one or the other all the time.
All the time. You're guaranteed it's one or the other.
Okay.
And so whenever something is certain, guaranteed, there's a 100% chance it'll happen, then the answer is 1. Other questions? Okay, let's flip it over to the back side here and talk about the multiplication rule. We were just refreshing our memory on the addition rule here, that some of us didn't like so much. So I think you liked it better when you could count. But what if you had, 7,000 things in your sample space? I don't think I want to spend all day drawing 7,000 items, and I would forget one and not be able to find it. So that's why we care about the multiplication rule. So at the top it says recall this formula, if we just talked about it. What we're worried about now is how to find the probability of A and B. How to get this question that we were stuck on, how to get this probability of heads and correct without doing the sample space. Because what if there were 7,000 things? We wouldn't want to get all 7,000. So that's the question that we're trying to do, is how can we find probabilities that have an and statement in it? And so, same example is listed right above here. The probability the coin shows tails, we already talked about. Probability of tails was 1.5 or 1/2, I'll leave it as a fraction for now. And the probability that you guessed correctly on your multiple choice quiz? 1 out of 5. We did those two pieces separately earlier, right? Let me come back over here and point those out. We already did that piece and this piece as part of this calculation here, right? And then we also found tails and correct by looking at our sample space. That's the one we were just double checking. Christian was saying where'd the 1 out of 10 come from, right? We got that by saying there's only one option here. It was this guy. This was the only option out of my 10 that had tails and correct. So we know the answer is 1 out of 10, but look what happened. If we take those two probabilities, what Leanna said earlier, and I said not everyone knows this one yet. If we're looking for tails and correct, if we take the probability of tails times the probability of correct, what do we get? 1/2 times 1/5 is 1/10. So even if there had been 7,000 items in my sample space, I could have multiplied and figured out it was 1 out of 7,000. instead of having to write out your sample space. Writing out the sample space is no fun once you get past about 10 items, if you ask me. There's a homework problem, I don't know if I assigned it, but I was helping another student in the lab on it yesterday, where it said to list all the possible ways a family could have 4 children. You know, girl, boy, girl, boy, boy, all girls, and so forth. And the students, and you had to type them all in there into the My Stat Lab. Turns out there's 16 different possibilities. And you have 16 little boy, 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 girl, 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 boy. And it was like, keeping track of all of them gets messy. It's doable, but the multiplication rule saves us doing that work. Okay there? So Kevin said it briefly a little bit ago. He says, so when it's or, we add. Right, we talked about that when we started. When it's and, we multiply. And sometimes you have to slow down and restate the question to figure out which one you've got so you make you do the problem correctly. Questions up to there. We're going to do more practice with these in a second. All right, so in the middle of the page it says conditional probability. Conditional probability. It has its fancy symbols. I'll tell you how we read it and what it means. Probability of B/A. It's a straight line, but that's supposed to be there, like a straight line. I can't draw it straight though, because I'm me. It's the probability that B occurs given that A has already occurred. We say the probability of B given A. I'll tell you what I mean by that. Let's see, we don't have much room to squeeze it in there. Maybe you can squeeze it off to the right side on your notes. Let's say A is the event that your car started today. And B is that you were on time to class. I'm just making up 2 events. One is that your car started. If you don't have a car, whoever gives you a ride. Anybody who walks, I'm sorry, I'm excluding you from this example. For those people who come in cars to school, A is that the car started, and B is that you're on time to class. If I just ask you for the probability of B, a typical student, what do you think the chances are of typical students on time to class? We're all a little bit different. How often do you think people make it to class?
90%.
90% of the time you think people are in class on time? I think that's fairly accurate. Agree with him?
Yeah.
So I think the probability of being to class on time is 0.90. I wish it was higher, but hey, reality happens. Some of us aren't as high as that. I'm not picking on anybody. Okay? Some of us are always here early. But what would this be? Let me tell you how to read this. Find the probability that you were on time to class today, given that your car started. If you know your car started, that's probably about the same, right? If your car started. So that might still be 90. But what if I gave you this? The probability of being on time to class given your car didn't start.
Would you subtract that from 1?
Well, it's not even subtracting from 1 because there's other factors that might be in there. But the point is, it's going to be a different probability though, right?
Probably be 10%.
It could be 10%, I mean, it could be 5, it's not exactly 1 minus that because these aren't exact complements because there's other factors. We have a 90% chance even if we walk maybe, right? So the car might not affect it. If your car started though, it doesn't change the probability, but if your car doesn't start, hey, maybe you live close enough, you still could have made it, you could have walked. So it wouldn't necessarily be all the way down to 10%. Some of us maybe could have made it, some of us would be at 0 for sure because you live in, I don't know, Richmond. I don't know why you're coming to school in Brentwood if you live in Richmond, but hey, maybe you do and there was no way you're going to get here in time. So then it would have been 0. But we all agree this would be something lower. I don't know, maybe it would be as low as 40%. Depending on where you live, that number might change for each person. But my point is, when you ask this question, given some other information, it changes the probability. I could say, how likely are you to get an A on the next test? Given that you got an A on the first test. Well, if you know the person got an A on the first test, they're probably likely to do the same thing, as opposed to the probability you'll get an A on the next test given that you failed the first test. Now, you still could, I'm not saying you won't, but that extra information kind of changes the likelihood based on whatever happened before. So that's what that conditional probability means. We're going to be seeing a lot of that in the next couple sections. We're going to use it here with this beautiful picture I drew. Okay, so I'm on example 1, middle of the page there. We have a box containing 5, it's supposed to say white marbles. Did you say white or wild?
Wild.
Mine too. I thought I corrected everything in here, but apparently not that. 5 white marbles. I've drawn them here. This is my fabulous artwork. Here's my box with 5 white marbles in it. 2 green ones. 8 blue ones. And 4 red ones. That last one's about to fall off the top, but I got it in there. It's not falling out yet. So I just drew all those marbles in the box. Imagine that they're all in there and I mixed them all up. And then we're going to close our eyes and start reaching in there and taking out the marbles. Okay, so we have this example. And we're going to choose 3 marbles, as 3 marbles are selected. And if you look at our notes, it talks about with replacement and without replacement. So I'm going to choose 3 marbles twice. I'm going to do this problem. Every problem here is going to happen twice. The first time I'm going to choose a marble, look at it, and then replace it back in there, put it back. Then I'm going to choose a marble, look at it, and put it back. And do that 3 times. That's called with replacement, meaning you put it back after you look at it. So we're going to do the with replacement part first. Let's do that right here. So the first one is the probability that all 3 are red. And I'm doing with replacement. I want to know how likely it is that I reach in there, I look at one, I put it back, I look at one, I put it back, I look at it, put it back, and every time they were red. Do you think it's likely or unlikely to happen?
Unlikely.
Why do you think it's unlikely? There's only 4 red ones. So it's hard to get a red one in the first place. And then to happen 3 times in a row, it'd be pretty unlikely. So we're expecting a small probability for our answer. Here's the big thing. This number 3 is not going to go in our answer anywhere. Everybody wants it. Like, there's a 3 there. It's 3 over something. It's something out of 3. The 3 is not going to go in our answer. Whenever we're asking questions about groups of things or people or things happening one after the other, the coin and then the guessing on the quiz question, you want to think about them one at a time. So I'm going to beat this up and I'm going to write it out by saying this is the same as saying the first is red and the second is red and squeeze it down here. The third is red. Red has a D. We agree that's the same thing? If we're saying that we want all 3 of them red, I'm going to beat it up and say I want the first one to be red, and the second one to be red, and the third one to be red. Why do you think I wanted to stress those ands so deliberately?
To multiply.
It tells me to multiply probabilities. So the biggest hint I can give you is anytime they're asking about groups of things happening one after the other, don't think of it as a group of 3, think of them one at a time. So what I'm going to do is multiply 3 probabilities. So, let's talk about when I reach in there, when I reach in this box full of my marbles here, what's the probability that the first time I reach in there, I get a red one? 1 out of how many?
19.
There's 19 total marbles in there? You guys counted for me? So there's 19. I don't think it's 1 though.
4,
Why is it 4?
because there's 4 red marbles.
There's 4 red ones. Remember, the denominator is your total, and your numerator is how many ways that your event could happen. So how many reds could I choose? There's 4 different red ones. So there's 4 out of 19 is the probability that when I reach in the first time, it will be red. And tells me to multiply by the next one. So remember, we're doing it with replacement. I pulled it out, I looked at it, oh, look, it's red. I threw it back in. What's the chances the next time I get a red one? It's still 4 out of 19 because I replaced it, right? Because I put it back in. And the third time will also be 4 out of 19? When you want to type this into your calculator, the easiest way to do it, some people like to multiply all the tops, multiply all the bottoms. I just type it in exactly the way I see it. 4 divided by 19 times 4 divided by 19 times 4 divided by 19. You can use exponents if you want. Let's see if we can type that in or see if we can all get the same number as an answer there, as a decimal. Anybody got it?
0.0093.
Someone agree with Christian?
Yes.
0093? If you don't agree with that, at the break, ask me how to type that into your calculator, and I'll help you with that. So I asked earlier if it was unlikely, and Kirsty said yeah, because it's hard to get all three of them to be red. Remember our definition of unlikely from last time?
5%.
Anything smaller than 5%, smaller than 0.05? This is definitely smaller than 0.05, so it's really unlikely to get 3 reds in a row if I reach in there. Okay, so what's the next question?
The first is green.
I'm gonna do without. I'm gonna do all of them with replacement, then I'm gonna do without. First is green, and the second 2 are blue. So I'm gonna go ahead and rewrite that with and statements from the get-go. First is green, and oops, and I put my A before my N there. And the second is blue. And the third is blue. Some of you will think I'm being tedious by writing all of this out, but when you go to do your lab assignments and your homework, writing out these statements with the first one and the second one and the third one makes it a lot more obvious what you're supposed to do. By the way, how did this 3 play into that problem we did the first time? Where'd that 3 come in?
3 times.
There's 3 fractions she set up here. I multiplied 3 different probabilities. The number 3 is not written in there, but the 3, that tells you how many things you're multiplying. When you have groups of things, it's not that that 3 goes in the problem anywhere. It says you have to look at them one at a time and you multiply 3 things. Okay, so I'm reaching in there. Probability that I get a green one.
2 out of 19.
2 out of 19, because there's 2 greens. And I'm still doing with replacement, so I throw it back in, mix them back up again. The next one has how many blues? 8 blues out of 19. And then the last one, I put it back in, still 8 out of 19. We're multiplying those. And you guys are gonna all punch your calculators for me and tell me what we get. Let's round it to 4 decimal places again.
0.0166
0166?
or 65.
6, 7.
I heard 5, 6, or 7. Which one is it? The last
Are you
digit.
rounding?
7.
Round it to this place. Is it a 7?
187.
It's a 7.
It's
I was-
187.
Yeah.
187.
Oh wait, oh there's no 6 at all. No wonder I'm confused. 0187?
Yeah.
That's what I got.
That's hard. Yep. Is that unlikely?
Yes.
Yeah, why is it yes?
Is less than 5.
That's less than 0.05, so it's unlikely for me to reach in and get a green followed by 2 blues. It's possible, but it's unlikely. It's unlikely just from the get-go, because it's hard to even get the green one, let alone 2 blues right after it. And then finally, let's do the third one. We'll take our break and we'll come back and do without replacement. All three are green. See if I can squeeze it down here on the bottom. I'm gonna even shorten. I'm gonna put green and green and green. What are my fractions going to be?
2
2 over 19,
2 over 19.
2 over 19, 2 over 19. By the way, if you like to use exponents, you could type this into your calculator like that. Same one we could have done with the first one. As long as you use your parentheses correctly and your exponents correctly. I expect this to be very unlikely. Hard to get 3 greens in a row because there's hardly any greens in there. What do we get?
0, 0, 1, 2.
0, 0, 1, 2? So that's the least likely thing to happen out of everything we did. Yes, sir?
How'd you get 3 greens? There's only 2 green in
Ah, because I'm replacing them every time. So remember, I'm pulling out the first one, going, yep, it's green, and then I throw it back in. And then I'm gonna reach in again, and it's gonna be, oh, I can get a green again. So you're right, if I wasn't replacing them, could I get 3 greens?
No.
No way, we're gonna find that out after our break. Other questions? Yes.
What's 3, nice how you asked, like, that's just how many times, like, you're filling back in the bag.
Yes.
That has anything to do with, and then how that's many fractions.
Exactly, so that's what my big point was. That number 3 just tells you that you have to think about them one at a time and end up multiplying 3 fractions. That number 3 doesn't really go in there
Okay.
at all, and that's the hardest part is your brain goes, well, I didn't use the 3,
Yeah.
but actually we did because we did 3 fractions.
Okay.
Okay, let's take a 10-minute break. We'll come back, we'll do the same problem without replacement, see what happens.
Like it's covered in I have one for now. I have one here, but I really outlay them because scratch them. And then I have one here. Not working yet. Wrong texture. Not too far from concentration. My cheeks used to be the out, and now it's actually for junior or senior year. But that's when I started getting it there bad. I've Did you study a lot?
Okay, guys, we got more to do, whether or not we want to. We're gonna pick up where we left off. The same problem we were just doing before the break? About the box of white marbles, blue marbles, green marbles, all that? Same problem, we're gonna do the exact same problem, we're gonna pull out 3. The difference is, we're not gonna put them back. So I'm gonna pull out a marble, look at it, say, oh, I like that, I'm gonna put it in my pocket. It's a really big marble, but I'm gonna put it in my pocket. Everyone okay, there's a subtle difference there, without replacement? I rewrote the problems over here just because I can't see all the way over there. You have them on your page. So the first one's red, and the second one's red, and the third one's red. The first time I reach in there, we already did this problem. There are 4 red out of 19. Right? That's for the probability of the first one being red. Everyone clear where we are? We're just off to the right side of this page now, but without replacement. I pulled out a red one. Oh, look, I got a red one. I put it in my pocket.
The
What's the-
denominator changes.
The denominator changes, she says. Because now how many marbles are left in there?
18.
There's only 18, right? Maybe I happened to get this one because it was right on top, right? That one's gone now. So we agree that there's now only 18 marbles left? How many of them are red?
3.
3. Right, because I took one of the red ones out. So now I've got 2 red marbles in my pocket.
Let's go to the one.
What's the chances that the next one will be red? How many marbles do I have to choose from now?
17.
Only 17 marbles left, and how many red ones will be left?
2.
2. But notice what happens if we don't replace them, the probability changes every time. Let me use some statistics words to talk about what we just did. This was the probability that the first one was red. This is the probability that the second marble is red, given that the first one was. Let me say that again. This is the probability that the first marble was red. This is the probability that the second marble is red, given that the first one was red. Knowing that it was red changed how many red ones I had left, as well as how many were left in there. Everyone okay with that statement? And then again here. This is the probability the third one is red, given that the first 2 were. So I know that I'm losing numbers of red and losing my total down here as well. I'm not worried about what the decimals are right now. I'm more worried about setting it up. So I'm just going to keep setting these up. I'm assuming you can punch those numbers in there. We'll get that in a little bit. So what's going to happen when I do the second one? First one being green. I'm doing green and then blue and then blue.
219.
2 out of 19. Because there's 2 greens out of 19.
8 out of 18.
She says 8 out of 18. Because there's 18 marbles left, but there's still 8 blues in there. I didn't take any blues out yet.
And then 7 out of 17.
And then 7 out of 17. If you don't know where these numbers are coming from and you're just copying them down, you need to ask me a question. Like yesterday. For now, would be good. Okay, let's talk about the third one. We talked about it before the break. Hector asked, well, how can you get 3 greens? Can you get 3 greens?
No.
No.
There's no way I can get 3 greens if I'm not putting them back. So let's do the math anyhow because I'm a total math nerd. The first time I reach in there, how many greens are in there? 2 out of 19. When I go to reach in there again and get another green one,
1 out of 18.
there's only 1 green left out of 18.
0 over.
And then the last one, there's no greens left out of 17. And when I multiply by 0, guess what I get? 0. By the way, you could have just said 0 on the test. Impossible, 0. But if you didn't know it was impossible, maybe you couldn't count to 2, I don't know. If you didn't know it was impossible, the math would still back you up. Show that it was right. Anybody calculate these for me?
The first one is .0041.
Someone agree with her?
Yeah.
Yeah.
Okay, and?
Is .0193.
So we're okay with those? Okay, so the formal rules at the bottom of the page there. The formal multiplication rule says, that's why I made a point to say what we were doing. The probability of A and B is the probability of A times the probability of B given A. So when we did the one with the coin and the guessing on the multiple choice quiz, I just multiplied them together. I didn't really talk about conditional probability. But what does this mean?
Given that.
Given that A's already have.
Given the A's already have it, what were you going to say, Christian? Same
Same
thing?
difference.
So this is how likely is the second thing to happen given that the first one has. So like look at down here. This was the probability that the first marble was green. This is the probability that the second marble is green, given that I know I already got a green one the first time. right? We knew that, which is how we got these calculations here. So this actually was probability of the first being green times, I don't have room to fit it up here, probability of green given that the first was green. Right? We used the fact that we already got the green one to figure out the next probability. Whether or not you know how to write out the formula, I'm not worried about, but the most important thing here we talked about is the and the multiply. Questions? You got those? Enough with the marbles? There's a word called independent right underneath that rule. Independent events are ones that don't affect the probability of each other. So my example earlier about your car starting and you being to class on time, the car starting kind of affects whether or not you get to class on time. So those are not necessarily independent, unless you happen to walk. Anybody walk to school? Nobody? Nick walks. Nick walks, so whether or not the car starts is not going to affect how likely he is to get here on time. So in his case, they would be independent because they don't affect it, but for the rest of us, those would be dependent events. How about the coin and the quiz question? Does what I flip on the coin affect what happens with my guess?
No.
No, right? I'm just doing them separately. They're completely separate. One doesn't affect the other one, so those would be independent events, which is why I was able just to multiply the probabilities together. The marbles. When I wanted 3 reds, what happened the first time didn't affect the probability for the second time, and didn't affect it for the third time. Why did it not affect it in this case?
Because you're putting them back.
Because I was putting them back. Because I put it back, it doesn't matter what happened the first time. This happens a lot in statistics where you say, okay, a family has 7 boys. What's the probability that their next kid's going to be a girl? 1/2, right? I mean, it doesn't matter what already happened. Those boys don't come along and say, hey, this is what's going to happen next. I mean, right? It doesn't work that way. So, given that those happen, those are independent. But as soon as I started taking them out and keeping them out, this happening affected this happening, affected and changed the probability. So those would have been dependent over here. Okay, the difference between independent and dependent? Okay, and that's the very last statement. If they're independent, this is just the same as the probability of B. Because whether or not the car starts, Nick's going to come to class late or not, and it's not going to change anything. That's what we're talking about. Okay, so we're going to flip over and start on section 4.3, which puts 4.1 and 4.2 all together, and it's probably the hardest section of this chapter. The good news is we're going to do some of it today. Oh no, I have another problem there, sorry. I got another problem before we go there, and then it gets harder. We're starting 4.3 tomorrow. So I'm on page 44. Sorry, I missed page 44. 44, we're all there? Let me erase all these calculations. Page 44, example 2. Pretty good. We've been here for over an hour. We're on example 2. Moving right along. I'll talk about that rule up at the top here in a second. I just want to read the example first. So we have a batch of 125,000 calculators, and 32 of them are defective. Bummer. You know, they can't all be made perfectly. If 2 calculators are selected, find the probability that they are both working. They're not defective, they work. Uh-oh. I claim we can do it. What does the word both mean? 2 calculators, they're both working.
What are you putting them back?
That's a good question. Am I putting them back, she wants to
Or are you
know.
just picking them up?
So she wants to know, am I doing with or without replacement? The rule is, unless you're told otherwise, it's never with replacement. Because it doesn't make sense, if you're gonna reach in here and grab some marbles, you wouldn't look at one and throw it back. You'd probably just grab one, grab another one. So the assumption is it's without replacement, unless you're told otherwise. I'm glad you asked that. So I'm doing it without replacement. I'm gonna grab one calculator, see if it's good, and then grab another calculator and see if that one's good. Ooh, I just said it. Just said what we should do. If I want them both to be good, if we break it down to one at a time, we agree I want the first to be good, and she underlines the second to be good. Changing my verb tense as we go. We agree that's the same as saying they're both good. Again, that number two calculators, is not part of the problem. That just tells me I'm doing this twice, kind of like the 3 in our marble problem, right? One marble, another marble, another marble. So I just want the first time I reach into this box of calculators, oh yes, ma'am.
I wanted to
Oh, go ahead,
answer it.
go ahead.
So 32 are defective, so you minus that from 125.
Because?
Because the other ones are not defective.
Right, we need to find out how many are not defective, how many good calculators we have. So hold that thought and I'll let you keep going. So I need to take my 125,000 minus the 32, and I get, what do I get? 1,149,68?
Yep.
Is that right? And what is that number?
How many are working?
These are the working calculators. Okay, so keep going, Ariana.
So I took one,
Mhm.
the first one. Is it 1 over? Yeah.
Okay, so let's just talk about the first calculator. My first calculator, how many total calculators do I have to choose from? I have a box of calculators.
125,000.
Total calculators, 125,000, right, so that's my denominator. And out of those, how many of them are good? The number that you just figured out. A lot of people think that's always a number 1 up here, which is common, that's what you started with, right, Ariana? Because you think I'm only choosing one calculator, but the one calculator isn't the one, it's how many of them are good, or how many of them were red, or how many of them were green. Even though I'm choosing one, we need to know how many fall into our category here. Out of this many, how many satisfy what we want? There's this many good ones. So this represents the probability that the first calculator is good. I'm not done. What do I do next?
So we took that out.
Then you have to deduct.
We took that one out.
Then you have to change the top number.
Yeah, and I heard someone say times. Why am I doing times?
And.
Because of the and. I did the first one, so now I'm gonna do the second one. Let's do the bottom number first, but you're right, the top one changes as well. I had 125,000 calculators. Now I only have
124.
124,999 if I subtract one, because I took one out. And how many good ones are left?
Subtract one.
One less than this, right? Messy. See if we can get that to our calculator. When the numbers are that big, that's why I recommend sometimes dividing first and then multiplying again and dividing. Otherwise they get really big. I'm thinking it's gonna be really likely to happen, to get 2 good ones, because there's hardly any bad ones in there. So I think it's gonna start with a 0.9. What do we get?
0.9995.
3 9s and a 5?
I got something different.
How different?
9916.
9916, anyone agree with Carrie?
What was the first one?
9995. We're gonna double check your work. Nice try though. That's okay. Every once in a while I have this case and Carrie's like the right one, so we better make sure. But your popular vote says she's probably wrong. I can't remember what it was. I think it was last semester where the one person was like, wait, and I went back and looked and that one person was right. So She's gonna double check it and decide if she agrees with us or not. Make sure you didn't copy the number down wrong. Sometimes it's just that. So what is this?
Very much.
Very likely to happen, 99.95, almost 100% chance that if you grab two of them, they'll be fine. Not guaranteed, because there are some bad ones in there. Okay, so now let's go back to the top of the page about the rule I skipped over. We'll do the 10 calculators in a minute. The rule at the top says the 5% guideline for cumbersome calculations. Cumbersome calculations are calculations that just go on and on. It's like, oh, I don't want to type all this into my calculator. Okay, well, maybe we should start the next one about the 10 calculators. 10 calculators, all good. What would I have to do if I was doing it for 10 calculators?
Like that, would just be deducting?
Like that, but I'd have to keep deducting, and what would I end up with that I'd have to multiply out?
10 different.
10 different fractions. That's a cumbersome calculation. I don't want to do that. I'm already tired and I haven't even written it down yet. So I can start with this. I'm not going to write the whole thing because I'm lazy and there's a shortcut, which is what my point is. And I could keep subtracting, right? I could take one more away. I'm not going to do any more than this, I swear. I would have to write out 7 more fractions. Do you agree? So I'd have a total of 10 fractions. And then I'd have to multiply those all out and not make a mistake and get the correct answer. That is definitely a cumbersome calculation. Way too much work. So there's a nice shortcut. So the rule at the top says, if your sample size is smaller than 5% of the population, then you can treat your selections as independent. Treating them as independent means you can assume that the first probability and the second probability are the same. If you take out just a few of them, it won't make much of a difference. Let me show you what I mean by that. Can somebody calculate just this fraction right here as a decimal? Just this one? Just the first part?
0.99974.
3 nines?
Yes.
744? Can you calculate just this one?
0.999743998.
Ooh, so if you rounded, it would still round to 744, right? Did you ever hear what she said? She said it was 7439 something. But if you round it to 6 decimal places, they're the same. They're not identical, but they're so close that we actually didn't have to even write this new fraction. We could have just said this number is going to be the same every time. And it only works because we only took 2 out of 125,000 calculators. If you take a small number of calculators or things out of your group, it won't affect the probability enough for you to have to do this work. So in this case, we know the first answer here is this. We can assume that every single fraction is about the same. So instead of writing that 10 times, what could I do?
Power of 10?
Raise to the power of 10. Or I could just take the first one and raise it to the 10th power. Do me a favor and raise this one to the 2nd power. I bet you get the same answer. Raise this first fraction, multiply it by itself, raise it to the 2nd power. Check our work here. Yeah, if you round it, it comes out the same. She's nodding over here. This doesn't always work though. So I'm waiting for you guys to calculate that one for me. Use your parentheses on your calculator, makes life easier. Anybody get this answer yet? I still think it should be pretty likely to get 10 calculators that are good. Hardly any bad ones.
Same as that one.
Exactly the same? 9995? For 10 calculators? Really? No one's saying yes or no. Someone nod or disagree with him. Did anybody type this in their calculator?
Yeah,
7.997442947
Okay, hang on a minute, we got different answers. So I think maybe you were still checking this one. Were you checking this one? Let me write out what we're saying here. This one is the same as taking the first fraction, 6/8. Squared, because there were only 2 of them. This one has to be to the 10th power. And I don't have enough of us getting this right answer, so we need to figure this out, make sure we all know how to get it.
I did check that one.
Yeah, okay, that's what I thought. Tell me one more time.
997442947.
If I stop there, will that be a 3?
Yeah.
That's what I thought I heard. Raise your hand if you got this. Well, that's good, more than half of us. Who doesn't know where the heck we're getting this? We need some help with the calculator. Anybody? Gary, still? Where the the exponent button, good point.
It's under the clear button.
It looks like this, it's called a caret. It's like points up. Yeah, sometimes I think know where that is. You guys found it already? Good? Okay. Good point. So this doesn't always work though. If I had done that with my marbles, if I had done that over here, 2/19 to the 3rd power would not have been 0. Right? It would not have worked here. If I multiplied this 3 times, it would not have been the same. And so let's talk about the difference. The difference is, it's a 5% guideline. If the number of marbles or calculators or whatever you're looking at is less than 5% of your population, this works. My population in this case was 125,000. 5% of 125,000 is... Somebody can multiply that for me. 0.05. 6250? Someone agree with that? As long as I'm looking at less than 6,250 calculators, I can take a shortcut. And I'm looking at either 2 or 10. That's definitely less than 6,250. 10 is less than 6,250. Which is why I can go straight to the shortcut.
It's less than what?
The 6,250, which was 5% of the total. But if you go back to my marble problem, there were 19 marbles in there. I was going to say calculators. There were 19 marbles in there. That's 5% of 19.
0.95.
0.95? So as long as I'm selecting less than 1 marble, the shortcut will work. Well, I can't select less than 1 marble. 3 is not less than... less than 1 if we round it, right? I can't select less than 1 marble, which is why I had to actually multiply it out. My big hint for you though is when you're doing problems like this and you start realizing, wow, that's a lot of fractions and that's really getting messy, most likely the 5% rule will help you get to the answer. There are a couple problems on my stat lab where they ask you to check to see if the 5% rule applies, and if it does, they expect you to use it. If you don't use it, there's a couple times where if you did the actual answer versus the approximation, your last digit will be off just a little bit. I don't care on the exam which way you do it, the real answer or the approximation. But we treat them as if they were all the same, as if they were independent. Questions there? Okay, so now we're flipping over to 4.3 to start putting all of this together. Oh boy, it'll be fun. We're going to do some more of this on Monday as well. So let's see what page I'm on. Page 50. Page 50.
It's the same over there.
Okay, are you on to page 50? So let's recap before we move on. When we're doing probabilities with or statements, probability of this or that, we add. When we're doing probabilities with and statements, we multiply. When you see probability of at least one of you loves probability, at least one of us, we'll start with that, at least one of us loves probability, then that's another little trick that you need. And what we need to think about is the complement. So let's talk about this. I'm going to make the statement that at least one person in this room likes probability. What's the complement of at least one?
More than one?
Well, if I'm saying at least one person in here likes it, and that's not true,
No one likes it.
what'd you say?
No one likes it.
No one likes it then. But if you want to prove me wrong, if I say at least one of us, including me, because otherwise you'll be able to probably prove me wrong. If I say at least one of us likes probability, the only way you could prove me wrong is if nobody liked probability. If none of us liked it. Do we agree with that? So the complement of at least one is none. And it turns out that thinking about none is a lot easier than considering all the other options. All the other options would be maybe exactly one of us like probability. Or maybe there's two of us that like it. Or maybe there's three. Or maybe there's four. My at least one has like so many different ways that could happen. But there's only one way that everybody hates it, right? Nobody likes it. So we're going to use that none. You're going to see at least one hidden in all kinds of problems. You want to make sure you think about the complement when you see those. So we want to, so before we do example one, to find the probability of at least one anything. The probability of at least one of anything. We're going to first find the probability of the complement, and the complement we just said is none. And then subtract from 1. And the probability of none is always easier to find than the at least one, because at least one, like I said, there's so many. It's one person, or two people, or three people, or four people. You're adding all these different probabilities. Okay, example 1. A family has 5 children. Find the probability that they have at least one boy. At least one boy. Which means what? What are some options if they have 5 kids?
1 out of 5.
They could have one boy out of the 5 kids.
Have all boys.
They could have all boys.
There's a multitude
No
of them.
boy.
They could have 2 boys or 3 boys, or maybe the 3 boys are older and 2 girls are younger, or maybe it's every other. Like, I don't think I want to list these all. If we wanted to do the sample space, well, there's all boys. There's boy, 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 girl. Or maybe the girl's older. Or maybe it's 2 girls, a boy, and then 2 girls again. You see why I don't want to list all these? Turns out there's 32 of them. I don't want to list them all. So instead, because the problem says find the probability of at least one boy, I'm going to use what I just talked about with the complement. At least one boy. To find that probability, I'm going to take 1 minus the probability of, what's the complement of at least one boy?
No boys.
No boys.
Like 0.
So that's doing the same thing we just talked about in general. We still have to find this, but I tell you it's easier than what we were just doing. Everyone okay that that's the complement? And that's why I'm subtracting it from 1? So describe this family if there's no boys.
All girls.
All girls. Describe the children one at a time for me. The first child is a
Girl.
And, she pauses while she says and. The second one is a girl, and third one's a girl, and so forth and so on. So I'm gonna write this out. Girl and girl. You don't have to write all these ands, but I swear that's gonna help you interpret your notes later. Do I have 5? 1, 2, 3, 4, 5. We agree that's describing no boys? And because there's ands, what am I going to do with all those probabilities? Multiply them. Probability that the first child is a girl?
1 out of 5.
Careful, when you just have one, when you have a baby, 1 out of 2, right? It's a 50-50 chance out of 2 options. 1 out of every 2 is a girl. Has nothing to do with the 5. It's just that if there's a person having a baby, 2 options, 1 of them's a girl. Right? And, oops, dribbled that out, I was pointing. What's the chances the next child's a girl? 1/2. What's the probability the next one's a girl?
1/2.
1/2.
And another 1/2.
And another 1/2. And another 1/2. Notice the number 5 is not in here anywhere. Where does the 5 come into play? There's 5 fractions that I have to multiply. So I'm going to write that as 1 minus 1/2 to the 5th. Which is where that 32 came from. If you leave it as a fraction, it's 1 over 32. We whining about probability over there? Yeah? It's okay, it happens. As long as you're still alive and breathing, I'm okay. So what do we get? 31 out of 32 if you're doing a fraction, or if you did a decimal. What'd you get? Let me do decimal? Nobody?
Where did 32 come from?
875.
196,875? And then the question was, where'd the 32 come from?
32.
When we multiply fractions, we multiply straight across. 1 times 1 times 1 times 1 times 1 is 1. And 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So multiply those fractions out. So that's how I knew when I said if I was to list them all, there's going to be 32 of them. I've done this problem before. I knew there would be 32. So there would actually be 32 things listed here, and there would only be one of them that had all girls. But you would have had to list all 32 of them. This is why we like the multiplication rule. It saves us from having to make giant sample spaces. Remember my warning last time about probability is going to get hard? Today's the day it starts getting pretty hard. Because what happens is the concepts are getting thrown together. You have to understand how complements work. The 1 minus the complement, you have to understand that part. You have to understand how to take the fact that there's no boys out of 5 kids and turn that into a multiplication problem. Nowhere did it say and in the problem, right? So you have to know to take that group. And then you have to know how to use the multiplication rule and use your calculator correctly. Questions? The biggest hints here were the at least one. At least one. Anytime you see that, just start thinking, oh, let's think about the complement first, because none is much easier to calculate than all the at least ones. If you wanted me to count, there would have been 31 of them that had at least one boy. We would have had to list them all, and that's time consuming. And then knowing that because we had a group of 5, to think about them one at a time and multiply those 5 fractions. I feel like someone has to have a question.
How did you get the 31 over 32?
From subtracting here, this one? You get a common denominator. This right here, right now, is a 1 over 1. I multiply it by 32 over 32.
Oh, okay.
It's way easier if you do decimal.
Yeah, I don't care. By the way, if you happen to be doing a problem on my stat lab where they want the answer as a fraction, every once in a while they do, and you ended up with this answer, There's a math button on your calculator. Is it to the left? A little bit down on the left? Is that where it is? Someone have the calculator? Third one on the left. If you hit math, the very first thing looks like this, and it says frac. You just hit that, it turns your decimal into a fraction for
You gotta
you.
hit it twice,
Yeah, you have to do that, then you have to hit enter.
yeah.
You have to do frac and then enter, it'll turn your decimal into a fraction. If by chance you need a fraction, but I don't care either way. Yes.
The fraction.
This is our answer to the original problem. The decimal problem. So Samantha asked a really good question. Is that the answer? Yes, we're done with the problem. So, you have a question? Go ahead.
What does it mean?
Aha, so two questions. Is this the answer and what does it mean? Let's make sure we understand that because you'll be asked things like this on the exam.
Yes, that's the answer, and it means that they have a
I know it's hard to see.
32 chances to have a boy.
So out of every 32 families that have 5 kids, we would expect 31 of them to have at least one boy. 31 out of every, it has to be a family of 5 kids. Out of all the families with 5 kids, every time you have 32 families, we'd expect 31 of those to have at least one boy. Or you could think of it this way. There's a 96.8% chance that if you take a family with 5 kids, at least one of them is a boy. Which should make sense. If somebody has 5 kids, you'd expect at least one of them to be a boy. It's possible, but not very likely that it wouldn't be, right? Yes, ma'am?
I have a family of 5. I have 5 sisters.
Uh-huh.
It's all girls, so we're like that 1% chance that it doesn't happen.
Ah, no, it's not even 1%, it's 1 out of 32, right? So Kirsty's one of them. Her family has 5 kids, and they're all girls. There's only a 1 out of 32 chance of her family happening that way, because all the other ones have at least one boy. Does that answer those 2 questions? Okay, let's see if we can set up example 2. And we'll go from there. There's a student who's an overachiever, and it's not there, but it's implied, who uses 3 alarm clocks to be more confident that he'll wake up in time for his statistics exam. Told you he was an overachiever. And the reason he uses 3 is his alarm clocks aren't that good. They only work 90% of the time. Which is why he's got more than 1 alarm clock, you can understand. 90%, that'd be, you'd be late, 1 out of every 10 times, right? So he's got 3 alarm clocks. What's the probability that at least one of his 3 clocks will wake him up? At least one, because he doesn't need all 3. He really only needs 1, but he uses 3 in case none of them happen, one of them doesn't work. If all 3 work, that'd be best. He only needs 1. So what are the clues in this problem?
At least one.
The at least one. Probability that at least one works, right? At least one wakes him up. So the at least one tells you to
Minus 1 minus the complement.
1 minus the probability of the complement, which would be
That number.
not a number, but in words. None of them work, right? The complement of at least one working, is it none of them work? So describe these 3 alarm clocks one at a time for me. What's the first one gonna do?
Not work,
It's not gonna work. And
not work.
the second one's not working, and the third one's not working. You see how I stopped and looked at them one at a time with ands? It's not gonna say that in the problem. Because we're looking at 3 of them, that's what tells me to look at them one at a time. So this is the probability of not working and not working and not working. Okay. 1 minus, I got some multiplications to do here. What's the probability that the first alarm clock is not working?
Wait, what?
10%.
Oh, how do we get 10%?
Because 90% of the time it works.
We're used complements there also, right? We were given that the probability that it works is 0.90, right? 90% chance that one works, which means that the probability of not working is 1 minus 0.90, which is the 10% chance it won't work, right?
Or you just take 100 minus 90.
Yeah, if you think, yeah, a lot of people think in percents is easier. 100 minus 90 is the same as 1 minus 0.90. Whichever way you see it, I'm fine. But we actually need that number. Because what is the probability that the first alarm clock doesn't work?
110.
1/10 is a fraction. I'm just going to leave it as a decimal, since that's what we have in here. 0.10 is the probability that the first one doesn't work.
And the second one.
And the second one doesn't work. 0.10. And the third one doesn't work. 0.10.
Why put them in parentheses?
Just so I don't lose my decimals.
Just keep separate.
It's because I want to separate these dots
Right.
from the decimals, and I have sloppy writing. But they don't need to be in
When you do your
parentheses.
calculator, you don't need to put.
Yeah, you don't need parentheses for your calculator. It's just so that you can see the distinction between the decimals and my dots. Notice I didn't have to write a fraction this time. I wrote a decimal. As long as it's a probability, we're okay. This ends up being 1 minus 0.001, which is 0.999.
So, very likely.
Very likely, there's only 1 in 1,000 chance that he won't wake up. There's a 99.9% chance that he'll wake up from one of his alarm clocks. I want to point out, as you're packing up, how many different things just happened in this real short little problem we just did. We had to use the complement here to figure out the probability of not working. We had to use the complement here because of the at least one. And we had to do the multiplication rule. Yes, Kirsty?
So it's fair to say that you have to find the complement first before you can even answer the question?
Yes. Yep, exactly. We'll do a little bit more practice with these and go on to 4.4 next time. I'll see you guys in the lab. I'm going to the lab right now. You might want to come join me.
So that was.